we are going to learn about the Arlang distribution. And the Arlang distribution is a generalization of the exponential distribution. Okay? And in the exponential model, the interval is determined until the first event is generated, right? Do you remember that? But in the case of the Arlang distribution, we have to find out the interval that is until the rth event occurs. So this is the summation of the exponential distribution. The exponential and the Arlang distributions are based on the Poisson process. And this is the example. The failures of CPUs in large computer systems are often modeled as a Poisson distribution. And assume that the failed CPUs are repaired immediately and the mean number of failures per hour is 0.001. And in that case, let x denote the time until 4 failures occur. Okay? And what is the probability that x exceeds 40,000 hours? In that case, we have to calculate the probability of x when x is larger than 40,000 hours. Right? Right? And what is the mean? Mean is large E, large X is equal to lambda, and that is equal to 0.0001 failures per hour. Okay? And if we denote n here, that is the number of failures in 40,000 hours. Okay? We are going to denote the n. N is equal to the number of failures in 40,000 hours. This can be changed to the probability of n when n is smaller than or equal to 3. Right? Why? Because x denotes the time until 4 failures occur. And the problem was the probability that x exceeds 40,000 hours, which means that in 40,000 hours, there will be 3 or less failures. Okay? Right? So we have to calculate this problem. And this is following the Poisson distribution, right? So the Poisson distribution, in the case of the Poisson distribution, the probability density function is equal to E minus lambda x by lambda x to k power over k factorial, right? That is the equation. So to use this, we have to know about the lambda x first, right? The lambda by x is equal to 0.0001 failures per hour by 40,000 hours. Right? So that is equal to 4 failures. Okay? Okay? So this can be changed to the function of k is from 0 to 3, right? exponential minus lambda x by lambda x to kth power over k factorial, right? And we calculate the lambda by x here, that is 4. So this can be changed to 4, okay? Right? So this will be e minus 4 by 4 to 0th power over 0 factorial plus e minus 4 by 4 to first power over 1 factorial plus e minus 4 by 4 square over 2 factorial plus e minus 4 by 4 to third power over 3 factorial, right? So what is this? That is equal to 1. And that is equal to 1. So this is just e minus 4. Okay? And plus this is e minus 4 by 4. Okay? Okay? And plus that is the 16, right? So if the 16 is divided by 2, 8 is left here. So e minus 4 by 8 plus, that is the 64, okay? So this is the 3 by 2 by 1. So 2 can be eliminated by dividing 64 here. 32 is left. So e minus 4 by 32 over 3. Okay? So if you calculate this equation, the answer is 0.433. That is the answer for this question. So this is about the R-long distribution, okay? And so the definition of the R-long distribution is that the previous example here showed that if x is the time until the Earth event in a Poisson process, then the probability of x when x is larger than small x should be equal to the summation of k from 0 to r minus 1, right? And exponential minus lambda x by lambda x to kth power over k factorial. Okay? And this can be re-expressed by is equal to 1 minus the probability of x when x is smaller than or equal to small x, right? And what is this? That is the cumulative distribution function. That is large F and x. So we can have this relationship. And by differentiating the cumulative distribution function fx based on extensive algebraic simplifications, we finally obtain this probability density function, okay? So the probability density function of the R-long distribution is equal to lambda to rth power by x to r minus 1th power by e minus lambda x over r minus 1 factorial, okay? And it is the probability density that defines the R-long distribution. And now, I'm going to explain about the gamma distribution. The gamma function is replaced with the factorial function in the previous equation when R is larger than 0. So the gamma R, this is the gamma function, is equal to R minus 1. This is the denominator in the previous equation, right? And this is the integration of x to R minus 1th power by e minus x dx from 0 to infinite. And the probability density function, the fx is equal to lambda to r's power by x to r minus 1th power e minus lambda x over gamma r, now has the gamma random variable with parameters lambda and r, and those parameters should be larger than 0. So the gamma distribution is the case that this r minus 1 factorial is changed to the gamma function, okay? But the concept is identical with the all-along distribution, okay? So the gamma's mean and variance, if x is a gamma random variable with parameters lambda and r, the mu is equal to r minus lambda, and the sigma square, which is the variance, is equal to r minus r over lambda square. And what was the mean and variance of the exponential distribution? In the case of the exponential distribution, the mean was 1 over lambda, right? And the variance was 1 over lambda square, right? But in the case of the exponential distribution, we have to find out the interval until the first success is generated, right? But in this case, the all-along distribution, we have to find out the interval until the rth success is generated, which means that this is repeated r times, right? Okay, simply. So based on this exponential mean and variance, we just can multiply the r. This is the number of success, okay? So we can simply use these equations to calculate the gamma's mean and variance. The parameter lambda and r are often called the scale and shape parameters, respectively. And this is the gamma distribution graphs. And x-axis indicate the random variable, and y-axis indicate the probability density function. And what was the lambda? Lambda was scale parameter, right? So when we increase the number of lambda here, okay? Sorry. So r is the shape parameter, right? So in this case, when we change the r value of r from 1 to 8.3, the shape of the gamma probability density function is changed, right? Right? So the value of r here, this curve becomes more symmetric, right? As compared to this curve has a more symmetric shape, right? And in this case, the R value is larger than, the R value of this curve is larger than this curve, right? So R is normally called the shape parameter, and also the magnitude of this probability density function is influenced by the gamma here. So we normally say gamma is the scale parameter, okay? And this is the example about the gamma application. The time to prepare a microarray slide for high output genomics is a Poisson process with a mean of 2 hours per slide. In the case, what is the probability that 10 slides require more than 25 hours? That is the problem. in that case, the mean of 2 hours per slide, right? Mean is equal to 2 hours per slide. Okay? And we have to find out the probability that 10 slides require more than 25 hours, right? So in that case, we're gonna have the x, and x can denote the time to prepare 10 slides. Okay? We can have this value here, this random variable here. And also we can have the random variable n here that can denote the number of slide made in 25 hours. Okay? We can have these random variables here. And what is the probability that 10 slides require more than 25 hours? That is, the probability of x should be larger than 25, right? Okay? Right? And this can be rewritten as the probability of n when n is smaller than or equal to 9, right? Right? Why? Because we denote x as a time to prepare 10 slides. Find out the probability that 10 slides require more than 25 hours, which means that within 25 hours, we can only fabricate 9 or less number of slides, right? Right? So, this is also follows a Poisson process, right? And so this is the summation of k from 0 to 9 exponential minus lambda x by lambda x to k's power over k factorial. And here, what is the lambda x? We have to calculate this value first. But in the problem, the mean was 2 hours per slide, right? And to use this value to the lambda here, we have to change this to lambda is equal to 0.5 slide per hour, right? Right? Because we are going to use the random variable n here. The definition of the random variable n here is the number of slides made in 25 hours, which means that the lambda should be some value slide per hour. Okay? So the lambda x is equal to 0.5 slide per hour by 25 hours. Okay? And hour can be eliminated, so this is 12.5 slide. So this can be written as the summation of k from 0 to 9 e minus 12.5 by 12.5 to k's power over k factorial. And this will be e minus 12.5 by 12.5 to 0's power over 0 factorial blah 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 plus e minus 12.5 by 12.5 to 9th power over 9 factorial. Okay? And if you calculate this equation, the answer is 0.2014. Okay? So, this is the answer for this question. And what is the mean and standard variation of the time to prepare test slide? The large E, large X was R over lambda, right? Right? So, what is the R here? This was the R minus 1, right? So, R is 10. And lambda is 0.5 here, okay? So, 0.5, that is equal to 20. Okay? And what is the variance? To calculate the standard deviation, we first know about the variance, right? Because root variance is the standard deviation. So variance was R over lambda square. Okay? That is equal to 10 over 0.5 square. Okay? Equal to 10 over 0.25, that is equal to 40. So the standard deviation is the root Vx, right? That is root 40, and that is equal to 6.32. Okay? So this is about the gamma application. And the gamma application is based on the Arlong distribution, okay? And now I'm going to explain about the Weibull distribution. The Weibull distribution is often used to model the time until failure for physical systems in which the failures increases with time, or decreases with time, or remain constant with time. And which means that we have to find out the time interval until R's failures are generated, but the failure is changed according to the time also. So in this case, we have to calculate the problem based on the Weibull distribution. Okay? The parameters in the distribution provide a great deal of flexibility to model above system. And the random variable x with probability density function here is the Weibull random variable with scale parameter delta and shape parameter beta here. So the probability density function of a Weibull random variable fx is equal to beta over delta by x over delta to beta minus 1's power by exponential minus x over delta to beta's power. Okay? So this is quite complicated equation. If x has a Weibull distribution with parameters delta and beta, then the commutative distribution function of x is given this equation. Fx is equal to 1 minus e minus x over delta to beta's power. And if x has a Weibull distribution with parameters delta and beta, then the mean and variance of x can be given by this equation. The mean is equal to delta and delta by gamma function, gamma 1 plus 1 over beta. Okay? And this is not the multiplication, but it is the function, okay? And the variance sigma square is equal to delta square by gamma function 1 plus 2 over beta minus delta square by a gamma function 1 plus 1 over beta to beta square. So by using this equation, we can solve the wave distribution problems. And this is the example. The time to failure of a bearing in a mechanical shaft is modeled as a wave random variable with beta equal to 1 over 2 and delta is equal to 5,000 hours. And what is the mean time until failure? In this case, the mean value of the wave distribution was delta gamma function 1 plus 1 over beta, right? That is the mean, okay, of the wave distribution random variable. And what is the delta here? Delta is 5,000 hours. So this is 5,000 hours by gamma function 1 plus 1 over, what is the beta? Beta is 1 over 2, that is 0.5. So that is 0.5, okay? That is equal to 5,000 by gamma function 3, right? And what was the gamma function? The gamma R was R minus 1 factorial, right? Right? So this can be written as 5,000 by 3 minus 1 factorial. That is equal to 5,000 by 2 by 1. Okay? So this is 10,000. So this is the mean time until failure in this question. And what is the probability that a bearing rests at least 6,000 hours? This is the probability of x when x is larger than 6,000, right? And that is equal to 1 minus probability of an x is smaller than or equal to 6,000. And this is 1 minus the cumulative distribution function of 6,000, right? Okay? And this can be written as 1 minus exponential minus x over delta to beta's power, right? That's the equation for the cumulative distribution function of the wave distribution, okay? So the 1 can be eliminated, and this is exponential minus what is x? That is 6,000, right? And what is delta? Delta is 5,000 here, okay? 5,000. And what is the beta? Beta is 1 over 2, 1 over 2. So this is equal to the exponential minus 1.095. Okay? If you calculate this value, you can obtain this one. Okay? And the answer is 0.334. Okay? So, based on the wave distribution, we can solve this simple example. And this is the last chapter of the chapter 4, okay? Last part. This is about the log normal distribution. And the variables in a system sometimes follow an exponential relationship as x is equal to exponential w. And in the case, the random variable large x should be equal to the exponential large w. And if w has a normal distribution, the distribution of large x is called as a log normal distribution. Why? Because to have the w, we have to multiply the ln at both sides. Okay? So, the ln x is equal to just w. Okay? And suppose that w is normally distributed with mean theta and variance w square, then the cumulative distribution function for x is shown in here. The cumulative distribution function of x is equal to the probability of x when x is smaller than or equal to small x, right? We already learned about this. And this should be equal to the probability of exponential w when this is smaller than or equal to small x, right? Because the x is equal to exponential w here. Okay? And by using the w, the probability of w should be smaller than the probability of the w when w is lower than or equal to ln x. This should be equal to this equation, right? Right? Because to change the x to w, we have to multiply the ln at both sides. So, the cumulative distribution function of normal distribution can be expressed by this equation. Okay? And the w has a normal distribution, which means that we can use the appendix table when we use the standardizing method, right? So, if we change the w to the standard normal random variable z, that can be smaller than or equal to ln x minus the mean. What was the mean? Mean was the theta here, right? Over the variance was the w square, so the standard deviation should be equal to w. Okay? So, based on this equation, we can solve the problem by using the appendix table. Okay? And large x is equal to exponential large w, normal random variable, with the probability density function, as you can see here. The probability density function is equal to 1 over x by w by root 2 pi by exponential minus ln x minus theta square over 2w square when x is between 0 to infinite. And the mean and variance of x are as follows. The mean is equal to exponential theta plus w square over 2. And the variance is equal to exponential 2 theta plus w square by ew square minus 1. So by using these two equations, we can solve the mean and variance of the log normal distribution. And this is the graphs. The log normal probability density function with the theta when theta is equal to 0 for selected values of. And as you can see, according to the w square, when we increase the value of the w square, the log normal probability density function is moved to the left side, right? So the x indicate the random variable in here, and fx indicate the probability density function, and the log normal probability density function is influenced by the w square. Okay, and this is an example. The lifetime of a semiconductor laser has a log normal distribution with zeta is equal to 10 and w is equal to 1.5 hours. And what is the probability that the lifetime exceed 10,000? And we have to calculate the probability of x when x is larger than 10,000, right? And this can be re-expressed by 1 minus probability of x when x is smaller than or equal to 10,000, right? And this can be written as 1 minus probability of w, okay, when w is smaller than or equal to ln 10,000, okay, based on the log normal distribution. And this can be written as 1 minus p z, okay, smaller than or equal to ln 10,000 minus what is the mean? That is 10. And what is the w? That is 1.5. Okay? And if you calculate this value, this can be rewritten as 1 minus the probability of z when z is smaller than or equal to minus 0.52. Okay? And then we use the appendix table. Okay? We have to use the appendix table. And we know about this value, right? Based on the appendix table. And the value will be 1 minus 0.3 or 1.532. So the answer is 0.698468. That is the answer for this question. And what is the mean and standard deviation of the lifetime? The equation of the mean was exponential zeta plus w square over 2. So this is equal to exponential 10 plus 1.5 square over 2, right? That is the mean. And if you calculate this, we can obtain 67,846 hours. That is the mean. Okay? And to calculate the standard deviation, we first know about the variance. Vx is equal to exponential 2 zeta plus w square by exponential w square minus 1. And this is equal to exponential 2 by 10 plus 1.5 square by exponential 1.5 squared minus 1. And if you solve this problem, 39 billion and 70 million and 59,887. Okay? And we have to calculate the standard deviation. So we have to provide the root here. Okay? The answer is equal to 197,662 hours. Okay? So this is the end of the chapter 4. Okay. So we are going to study about the chapter 5. One nine six 662. And this is the chapter 5. The title of the chapter 5 is the analysis of joint probability distributions. Okay? And this is the chapter outline. The chapter 5-1, in this case, we are going to learn about the 2 or more discrete random variables. And firstly, we are going to learn about the joint probability distribution. And secondly, we are going to learn about the marginal probability distribution. And then we are going to learn about the conditional probability distributions and the independence and the multiple discrete random variables. And finally, we are going to learn about the multinomial probability distribution. Okay? And in the case of the chapter 5-2, we are going to learn about 2 or more continuous random variable. Okay? This is the discrete and this is the continuous. And in similar with the chapter 5-1, we are going to learn about the joint probability distributions of 2 or more continuous random variables and the marginal probability distributions and the conditional probability distributions and independence. To learn about the multiple continuous random variables. Okay? And after finishing the chapter 5-, we are going to learn about the covariance and correlation. Okay? Covariance variance is 공분산 in Korean. And after that, the book introduced about the bivariate normal distribution, but in this course, this chapter is not considered. Okay? And after finishing the covariance and correlation, we are going to learn about the linear functions of the random variables. Okay? And finally, we are going to learn about the general functions of random variables. So these are the chapter outlines of the chapter 5. Okay? And this is about the learning objectives. After careful study of this chapter, you should be able to do the followings. Firstly, we can use the joint probability mass functions and the joint probability density functions to calculate the probabilities. And in the case of the discrete random variable, we normally call the probability mass function, right? But in the case of the continuous random variable, we call the probability density function. Okay, do you remember that? And secondly, we can calculate the marginal and the conditional probability distributions from the joint probability distributions. And we can interpret and calculate the covariances and correlations between the random variables. And we can use the multinomial distribution to determine the probabilities. And then we can calculate the means and variances for linear combinations of random variables. And we also can calculate the probabilities for linear combinations of normally distributed random variables. And finally, we can determine the distribution of a general function of a random variable. So after learning of the chapter 5, we can do all these 5 things, okay? So I'm going to introduce about what is joint probability distribution. In the previous chapter 3 and 4, the probability distributions was for a single random variable, right? We only consider one random variable in the chapter 3 and chapter 4. But it is often useful to have more than one random variable, which means that we normally have 2 or more random variables in the identical system, okay? And for example, in the classification of the transmitted and received signals, each signal can be classified as high, medium, and low quality, okay? In this case, we might determine the random variable x to be the number of high quality signals and the random variable y to be the number of low quality signals. In that case, we have 2 different random variables in the system, okay? In that case, we have to solve this problem based on the joint probability distribution concept. If x and y are 2 random variables, the probability distribution that defines their simultaneous behavior is called a joint probability distribution, which means that they occur at the same time, okay? So this is the typical example to explain about the joint probability distribution. Using a cell phone to check your airline reservation, the airline system requires that you speak the name of your departure city to the voice recognition system. Okay? And in the case, let y denote the number of times that you have to say your departure city to the voice recognition system. And let x denote the number of bars of signal strength on your cell phone. And when you see your cell phone, there is a bar, right? According to the signal strength. So the x denote the number of bars of the signal strength on your cell phone, okay? In this case, we have 2 random variables, x and y, and we have to consider them at the same time, right? Because the number of bar signal influence to the number of times that we have to say our departure city to the voice recognition system, okay? And in that case, we can have this kind of table. This is the joint probability distribution of x and y. And this column indicates y. That is the number of times city name is stated from 1 to 4, okay? And at the same time, we have the random variable x here. That is the number of bars of signal strength from 1 to 3, okay? And in this case, these values are the joint probabilities, okay? And if you add all these values, the value is obtained, okay? And this is about the joint probability mass function. Because the chapter 5-1 is considering about the discrete random variable. So this is the joint probability mass function, okay? And the joint probability mass function of the discrete random variable x and y denoted as f, xy, and x, okay? And this satisfies, firstly, this is larger than or equal to 0. And the summation of this joint probability mass function is equal to 1. And the joint probability mass function can be expressed by this equation, the probability of x when x is equal to small x, comma, y when y is equal to small y. Okay? And based on the joint probability distribution, we can also think about the marginal probability distributions. And it is important to distinguish between the joint probability distribution of x and y individually. The individual probability distribution of a random variable is referred as its marginal probability distribution. And this can be understood more easily based on this example. The joint probability distribution of x and y in the previous figure 5-1 can be used to find marginal distribution. For example, what is the probability of x when x is equal to 3? So in the case, we have to calculate the probability of x when x is larger than equal to 3. In the previous figure 5-1, okay? And in this case, we don't have to consider about the random variable y, right? Which means that this can be written as the joint probability mass function of x when x is equal to 3 and y, summation from y is equal to 1, to 4. Okay? So this can be written as the probability of x when x is equal to 3, comma, y is equal to 1, plus the probability of x when x is equal to 3, comma, y is equal to 2, plus the probability of x 3, y is equal to 3, plus the probability of x when x is equal to 3 and y is equal to 4. Okay? So in this case, what is this summation? That is the summation of this column, right? Because this is the joint probability mass function of x when x is equal to 3 and also y is equal to 1, right? What about this? There is a joint probability mass function of x when x is equal to 3 and y is equal to 2, right? So this summation is the summation of this column, right? So the answer is 0.25 plus 0.2 plus 0.05 plus 0.05. That is equal to 0.55. Okay? Okay? So this is the marginal distribution. Okay? And the summary of all possible marginal probability distributions of x and y can be in this table. Okay? And what is this? That is the joint probability distribution mass function, right? Okay? This table indicates the joint probabilities. Okay? This is identical to the previous figure 5-1. But this column indicates the marginal probability distribution, okay? Marginal probability of y when y is equal to small y. Okay? For example, the marginal probability of y when y is equal to 1, they should be the summation of this column, right? So this column indicates marginal probability of y. And what about this? That is the marginal probability of x. Okay? So this is the marginal probability distribution table. And what is the marginal probability mass function? If x and y are discrete random variables with joint probability mass function, fxy, x comma y, then the marginal probability mass function of x and y can be written as follows. Firstly, the marginal probability mass function of x is equal to the probability of x when x is equal to small x. And they should be equal to the summation of y, right, of the joint probability mass function. Okay? This is the summation of joint probability mass function. Okay? So the marginal probability of y is also expressed by the summation of x of joint probability mass function. Okay? So where fx is the summation of all points in the range of x comma y for which x is equal to x, small x, and fy is the summation of all points in the range of x comma y when y is equal to y, small y. And after learning about the joint and marginal probability mass functions, we have to know about the conditional probability distributions. When the random variable x and y are independent, the probability of x is associated with the value of y, right? Okay? And it is called a conditional probability distribution. And recall that the definition of the conditional probability in the chapter 3 for events A and B can be written by this equation, right? The conditional probability of B given A is equal to the probability of the intersection of A and B over probability of A. Do you remember this equation, right? This definition can be applied with the event A defined to be x is equal to small x and the event B defined to be y is equal to small y. And this is an example. In the previous example 5-1, x and y denote the number of bars of signal strength and times you need to say your departure city respectively. And what is the probability that y is equal to 1 given that x is equal to 3? And the conditional probability of B given A is equal to the probability of A intersection B over the probability of A, right? So, based on this equation, we can have this problem. We can solve this problem. That is the conditional probability of y when y is equal to 1 given x is equal to 3. Okay? This is the identical formulation, but the b is transferred to y equals to 1, and a is transferred to x, which is equal to 3. That should be equal to the probability of x is equal to 3, comma, y is equal to 1, right? That is the intersection, okay? Over the probability of x when x is equal to 3. And what is this? That is the joint probability mass function, right? And what is this? That is the marginal probability mass function, okay? So, in the previous table, what is the joint probability of x when x is equal to 3 and y is equal to 1? That is 0.25 here, right? So that is equal to 0.25. And what is the marginal probability of x when x is equal to 3? That is the summation of this column, right? Okay. So that is 0.25 plus 0.2 plus 0.01 plus 0.05, sorry. So that is equal to 0.25 over 0.55. Answer is 0.454. Okay? So, to solve the conditional probability problem, we first know about the joint probability mass function and also the marginal probability mass function. That's why we already learned. And this is about the conditional probability mass function. Given discrete random variable x and y with joint probability mass function fxy, x comma y, the conditional probability mass function of y given x when x is equal to small x is given by this equation. And as I mentioned in previous slide, this is the joint probability mass function, right? And this is the marginal probability mass function. And this is the conditional probability mass function, okay? The conditional probability of y given small x, because when x is equal to small x here, okay? And y is, this is the conditional probability mass function of large y given x is equal to small x, okay? So based on this equation, we can simply calculate the problem. And because a conditional probability mass function f y given small x y is a probability mass function, right? The following properties are satisfied. Firstly, this value should be larger than or equal to 0. And the summation of the conditional probability mass function should be equal to 1. And this conditional probability mass function can be expressed by this equation also, okay? The probability of y when y is equal to small y given x is equal to small x. So these three properties should be satisfied. And this is about the conditional mean and variance. The conditional mean of y given x when x is equal to small x, denoted as the large E, large Y given small x, or mu large Y given small x, okay? That is equal to the summation of y multiplied by the conditional probability mass function, okay? And the conditional variance of y given x when x is equal to small x, denoted as large V, large Y given small x, or sigma square large Y given small x, is summation of y minus the conditional mean, okay, square by the conditional probability mass function, okay, or the summation of y square by the conditional probability mass function minus the conditional mean square. And this is the identical formulation with the probability mass function, right? Do you remember that? In the case of the probability mass function, the Ex was the summation y multiplied by the probability mass function, okay? And what was the variance? There was the sigma y minus the mean square and probability mass function. That was the case of the probability mass function in the chapter 3. And in the case of the conditional probability mass function, we can use the, but we have to change the probability mass function to the conditional probability mass function. That is the only difference. This is the example. In the previous example 5-1, what is the conditional mean of y given x is equal to 1? we have to calculate the large E, large X, 1, right? Because small x is equal to 1 here, okay? So to solve this problem, we first have to change joint probability distribution, the joint probability distribution table to the conditional probability distribution table. To calculate these two values here, okay? Because when we solve the mean of the conditional probability mass function case, we have to use the conditional probability distributions, right? So if the distribution was given in the problem, we first have to transfer the joint probability distribution table to the conditional probability distributions to solve the mean variance, okay? So I'm going to solve first. That is the conditional probability of y when y is equal to 4 given x is equal to 1. Okay? And that is equal to the probability of y x is equal to 1 and y is equal to 4 over the probability of x is equal to 1. Okay? And what is this? There is a 0.15 here. Okay? 0.15 over what is the marginal probability of x when x is equal to 1? That is the summation of this column, okay? So 0.01 plus 0.02 plus 0.02 plus 0.15. So that is equal to 0.15 over 0.2. Okay? So this is 0.75. Okay? So by using this process, we can simply make this conditional probability distribution table, and then we can solve this problem. And this should be the summation of y is equal to y from 1 to 4, right? Y by the conditional probability of y given 1, y. Okay? Okay? So this is the equation. So we have to solve this one. That is 1 multiplied by the conditional probability of y given 1, okay? And 2 by the conditional probability of y given 1 and 2 plus 3 by the conditional probability of y given 1, 3, and the conditional probability, 4 by the conditional probability of y given 1, 4. Okay? So what is this? X is equal to 1 and y is equal to probability, right? So x is 5. So there is 1 by 0.05 plus 2 by, what is this? So y is equal to 2, but x is equal to 1. That is 0.1 plus 3 by 0.1 here, okay? 0.1 plus 4 by 0.75. Okay? Okay? So if you solve this one, the answer will be 3.55. Okay? And we are going to solve the conditional variance in the next class, okay? So this is the end of today's class. See you next week, okay? There is no class on Friday.